Lesson 2, one-dimensional force problems. Cole, by one-dimensional force problems, I mean stuff that's in a nice straight line. In a couple of lessons, we'll start to go at an angle. Did I say angle? Yes, it will be components. We'll be bringing some of that in. But for now, we're going to keep everything in a nice straight line. It doesn't mean that some stuff won't be moving up, down at the same time as some stuff is moving left, right. It's just going to mean everything's going to be at nice 90-degree angles to each other, and we can compartmentalize it. What are some important one-dimensional force problems? The elevator problem, the apparent weight problem. I like that question. I like that question. I like that question. Air resistance. Air resistance I like, but it's really complicated in real life to analyze it properly. So we'll talk about it, but we'll deal with it in a kind of a unique way. Friction, we'll spend a whole lesson on friction. That's going to be the next lesson. And the many-body problem. The many-body problem. Pause for a second. So the normal force is the contact force between the floor and an object. That's not quite right, but we're going to start there. It's the contact force. It's a Newton's third law, reactive forces come in pairs force. Duncan, the reason the normal force has to be there is because of Newton's first law. When I'm standing here, is gravity acting on me? Yes, there is definitely a force down. Am I sinking into the ground like quicksand? No. Am I flying into the air like Superman? Then there must be another force in the opposite direction of gravity, same magnitude. Newton's third law, forces come in pairs. And I know it's the same size because if it wasn't, Newton's first would kick in and I'd be flying into the air or sinking into the ground. So the normal force is the force with which the floor pushes on you. And interestingly enough, the normal force is also the value that a scale would read. Scales do not read weight. They read Fn. They read Fn, the normal force. Put your pencils down. Back when we used to have provincial exams in Physics 12, I was marking Physics 12 provincial exams one year, and at another table over there, they were marking a question, and the question said this: find Fn, the normal force. And a kid had written this: which was funny, but it didn't get him any marks at all. He got a 0, but we laughed, and then okay, whatever, he got a 0. This is why the normal force is often called the apparent weight, not your true weight. Your true weight is mg. The apparent weight is what you feel from the ground pushing up against you. In fact, any good amusement park ride, Chelsea, any good amusement park ride, Kayvon, mucks around with the normal force. You like it enough, you'll pay money for it. You like it enough, you'll pay money for it. How many of you been on the elevator before? Okay? The elevator. Does your mass change on the elevator? Do you gain atoms or lose atoms when you're on there? No. Why do you feel heavier and lighter? We change the normal force. We change the normal force. It's what any good roller coaster does. Any good roller coaster mucks around with the normal force. What you think of as how heavy you feel is actually the ground, or right now your chair, pushing up against your body. If that chair vanishes, I'm telling you, mg is still in effect. You'll fall down for a brief moment, you'll feel weightless. But you're not. The apparent weight is the ground pushing up against you, the normal force. Example 1. Suppose a person with mass m and weight w is in an elevator standing on a bathroom scale, but our scale is going to actually not measure in kilograms. It's going to measure in newtons just to make life easy. So a real physics scale that measures in newtons of force. If the elevator starts at rest and accelerates up, I would probably underline that, and I would probably underline that. What will the scale read? W, more than W, or less than W? If someone's standing on a scale, they have mass M, weight W, and the elevator starts at rest and begins to accelerate up, what will the scale read? W, more than W, less than W. You know what? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. Positive, meh. Dueck will make fun of me if I don't vote, so I'm going to put my hand up when I just kind of go with the flow. Who says A, it'll read W, it'll be their weight? No one. Who says B, more than W, it'll read more than their weight? Who says C, less than W? Who didn't bother putting their hand up at all? Because they had no courage and no conviction. Take a risk in my class, my angel, my child. The majority suggested B. Convince me. Yeah.
If it's accelerating up, then the winning force has to be greater than the losing force. So the normal force is going up. So the normal force has to be greater than the force going down, which is...
I love the explanation, except way too much English. Blah, 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 blah. You know what? I think a picture is worth 1,000 words. I think this is a job. This is a job for a free body diagram. Let's represent this person with a dot. Right there. What are the forces acting on this person? Get the obvious one. Now, normally I'd call that mg, but what did they call the force of gravity in this question? I'll use a W for weight. I'll use their notation. Okay. Is this person in free fall? In fact, which way are they accelerating? That means there must be a force up. What force is that? It's the scale pushing up against them. It's the floor pushing up against them. It's the normal force. Doug, how will I draw the normal force compared to W? Bigger, smaller, or the same length? Why? Okay, Duncan, what's my equation? Who's winning? We said our approach is going to be winner, takeaway, loser equals MA. I think the normal force is winning, so it's going to be winner. Oh, yeah, that's right, Mr. Dueck. Takeaway, loser, that equals MA. How would I get the normal force by itself? Why does that mean that the normal force has to be bigger than W? Algebraically, what does that mean? Mathematically, what does that mean? If they were the same size, the equation would look like that, right? So why does that mean that it has to be bigger? When you add something, what happens to your answer? It's got to be bigger. When you add something, it's got to be bigger. And this is what Duncan said. I'm just doing this with no English. I'll even do a nice therefore. Remember, anytime you see a therefore, make sure you know what it's therefore. Fn has to be bigger than weight. Has to be. Why? Because you're starting out with the weight and you're adding something to it. This number must be bigger. Must be. Hey, while we're on this topic, what if the elevator was moving up at a constant speed? What would your acceleration be? Zero. So what would happen to this term right here? Vanish? Oh, you would feel nothing. And this is what Einstein said. He said, you know what? If you're in outer space, inside an elevator with no windows, you can't tell if you're moving at a constant speed or standing still. It's impossible. There is no physics way to tell the difference. In which case, it means that speed is relative. This is what started him thinking about speeds and lights and what acceleration was, and he suggested that maybe gravity could be treated the same as an acceleration, and he went from there. Example 2 says write a net force equation. We just did. Right there. So let's crunch some numbers. Example 3. A 35 kilogram student stands on a kilogram scale. Now, if we want an answer from a scale in kilograms, how do we go from kilograms on a scale if we know the normal force? We take the normal force and we divide it by 9.8. To go from newtons to kilograms, divide by 9.8. To go from kilograms back to newtons, times by 9.8. That's how scales are calibrated. Kilograms are literally the force of gravity divided by 9.8. That's how they're calibrated. So, if the elevator accelerates down, I'm probably going to underline that, then find the A, normal force, B, scale reading. Hey, what's the first thing I'm going to do here? Doug, what? This is a job for a free body diagram. I'll do mine right there. There's the person. What are the forces acting on this person? Get the obvious ones. Is this person in free fall? So there must be a force acting in the opposite direction. Which force? See how we're using newtons first, right? Which force? The floor pushing up, which we're going to call the normal force. Should I draw the normal force bigger, smaller, or the same? Which way is this person accelerating? Down, so I know down must be winning. So I'm going to draw the normal force smaller. Smaller. Who's winning? So again, we're going to go back to our winner minus loser equals MA. We're going to say this is going to be gravity minus normal force equals MA. What did part A want us to find? Sanj, what did part A want me to find? That. How could I get that by itself? Sanj, I think the easiest, what's in front of the normal force right now, Sanj? I think plus this to this side at the same time minus that to that side. Can I do that in one step, okay? Is that all right? Is that all right? Is that all right? We're going to get this then. mg take away ma equals the normal force. We're going to get the normal force equals, now let's do a quick double check. Can we solve this? Sanj, do we know the mass? Yep. Do we know G? 9.8. Not negative anymore. In this unit, we've decided to take care of the direction by using our winner minus loser. Don't ever put a negative 9.8 into a force equation in this unit. Do I know the mass? You already said that. Do I know the acceleration? Oh yeah, there is a meters per second squared. Oh, we're home free. Plug and chug. Mass, 35. G, 9.8 minus mass, 35. A, 2.25. What do we get? Let's see. Normal force is how big? You get 264.25 to 3 sig figs, 264 newtons. B. B. Neve, what does B want me to find? How can I find the scale reading in kilograms? First of all, what does a scale measure? Does it measure mass? Say no. What does a scale measure? What does a scale measure? Normal force. Did we find the normal force in part A? Okay, now they want us to go to kilograms. How do I go to kilograms? Take the normal force, Neve, and divide it by? Oh, we can do that. Scale is going to be normal force divided by 9.8 divided by 9.8. So the scale is going to read 27 kilograms. Is that their actual mass? No. What's their actual mass? So here's the question. Will this person feel heavier or lighter? This is what's going on the elevator when it accelerates down. The reason you feel like you're going to fly out of your seat, you're not. In fact, I'm fairly sure you could do that ride without any restraints whatsoever, and you'd be perfectly fine, except for the fact that you'd probably tense up and slide off the chair as your body wanted to straighten out in fear. I think the restraints are purely to keep you from doing something dumb. But I think in terms of the actual accelerations, you're never in any danger of flying off that chair, because the net acceleration is still down. It just feels so freakish to you because you've never experienced a chair, you've never experienced that feeling of lighter, and it's built into us. We don't like falling. There's a reason why one of the most common nightmares is falling off of a cliff, or the fear of, you dream of it. It's built into us. Built into us. And in fact, we're much more okay with higher normal force because we experience that fairly often. Whenever you carry something, you actually feel a bigger normal force through your feet. We experience that all the time. And that's why on the way up, not as scary. It's on the way down that you get the huge adrenaline rush. That's why on the roller coasters, what's the scariest part of the roller coaster? The first hill. Why? That's when you're getting a lower normal force than you're used to. That's when all your body's safety mechanisms start to kick in because it thinks you're falling and it thinks that's bad. That's what we pay for. Going up the hills, you're getting pushed down. Sorry, you got to be careful. You're not getting pushed down into your seat. It feels like you're getting pushed down into your seat, which really means you're getting accelerated upwards because our bodies are backwards accelerometers. But you know what? That one we're fairly casual on. I mean, we like it, but it doesn't terrify us as much. If you're ever on a roller coaster sometime, notice when people scream. On the way down, not so much on the way up. Yeah, I actually noticed those things. Sorry.
You've wrecked the ride for me forever.
Put your pencils down. So we've talked about the normal force. Force number 2, air resistance. Air resistance is the force of air molecules bumping into an object that's moving through the air. And the force of air resistance has direction opposite to motion. If you're moving forwards, air resistance is backwards. If you're moving backwards, air resistance is forward. Problem is, air resistance is a really complicated force, and we'll talk about why, but let's do a small example here. So it says, do a free body force diagram for each of the following. What we're going to do, there's my tennis ball. We're going to imagine situation A, a ball is being thrown. And K-Von, what we're imagining here then is, situation A is while it's on its way up in my hand. Situation B is on the way up in the air. Situation C is on the way down in the air. Okay? You've all thrown something up and caught it. So let's talk about the physics here. It says draw a force or a free body diagram. Okay, we can do that. Oh, too far. So let's do situation A. Let's represent the mass with the dot. What are the forces acting on it? Get the obvious one. Really? Okay, mg down. While you're throwing a ball, while it's in your hand, which way is the ball accelerating? So there has to be a bigger unbalanced force up. I'll call that, F throw. I don't know. You could call that perhaps some kind of a normal force because it's a surface, but I like to think of a normal force as coming from an inanimate, dead surface, and as far as I know, I'm still alive. So I'll call it F throw. You could argue there's some air resistance. I'm going to say that my hand is absorbing it all. I'm going to ignore air resistance for now. Keep it simple. On the way up. You saw it? What are the forces acting on the ball on the way up? Get the obvious one. What else? Air resistance. F air. Which way? Which direction is the ball moving? So which way is it? And you know what? I'm going to draw it then, I guess, right next. It's not that big, but it is there. I just can't quite draw it on the same line because then it looks like they're overlapping. So, Stephanie, I just drew it over a little bit, right? There's two forces down. What about on the way down? What are the forces acting on it? Get the obvious one. What else? Which way would air resistance be acting this time? Okay. Now, there's a problem with air resistance if we want to do it properly. If we want to do it properly, air resistance changes all the time because the faster you move, the bigger the air resistance, the quicker it slows you down, the smaller the air resistance, the faster you can move, the bigger the air resistance, the quicker it slows you down. You really need calculus to do it properly. You need drag coefficients. You need to know the surface area of the object you're talking about. It's complicated, very complicated. What we're going to do, Enzo, to simplify it, is we're going to use winner minus loser and kind of treat it like we did friction last year. Oh, by the way, turn the page. Example 5 says this. In example 4b, I'll go put 4b back on the screen in a second. How can the ball be going up in diagram 4b? How the heck can the ball be going up if all of the forces are down?
It's deaccelerating.
For me?
It's deaccelerating.
Deaccelerate? That's a word. Explain.
Well, you have initial velocity up.
Yeah.
So it has that. It's slowing down because gravity and the F air is
Right? Velocity and acceleration don't have to be in the same direction. In fact, every time you hit the brakes, I'm telling you, your velocity is forwards, but your acceleration is backwards. Eventually, if you keep accelerating, your velocity will end up in the same direction as the acceleration, because eventually that's the direction of your change in velocity as well. But it's perfectly acceptable if you're traveling up and purely accelerating down. It's what happens every time you throw something up. It's why it comes to a stop at the top of its arc for a split second. I'd take yours, but I wanted to think of something short. Okay. Example 6. If the ball in example 4c right here is speeding up, write a net force equation. Okay. Who's winning?
Depends on.
Who's winning? No depends. Who's winning? Gotta be. It's accelerating down. Who's losing? Your equation would look like this. Gravity, take away air resistance equals ma. Doesn't depend. I'm fairly certain.
I thought you said. Sorry.
That's okay. Example 7. A 70-kilogram parachutist. Oh, he jumped out of a plane. Eventually, I jumped out of an airplane. 90-kilogram parachutist. Free falls for a time and then opens the parachute. If the parachutist slows down at a rate of 1.5 meters per second squared, A says, compare the forces that act on the system. That's fancy physics talk for write yourself a free body diagram. B says, write a force equation. Hopefully that's going to come out of a good free body diagram. And C says, find the force of air resistance on the parachute. Okay. A. There's the parachutist. What are the forces acting on the parachutist? Get the obvious one. Now, think carefully. We did see a video the other day of some idiot jumping out of an airplane, yours truly. When I pulled my parachute, which way do I accelerate? Which way am I? Doug, convince me. Doug says up, convince me. Which way is my velocity? Am I slowing down or speeding up when I pull up my parachute? So that must mean the net acceleration up. Same way as when you're driving forwards and you hit the brakes to slow down, that must mean you're accelerating backwards, even though your velocity is forwards. Okay, so what are the forces acting on the parachutist? Get the obvious one, gravity. Is the parachutist in free fall? Not anymore. Pulled the parachute. So there must be a force up. Is it bigger or smaller than mg?
Bigger.
Small.
It's bigger because otherwise it'd still be accelerating down.
Which way am I accelerating? So is it bigger or smaller? Why must it be bigger? Because if it wasn't bigger, there's no way that I could be accelerating up. I'd be dead. It's got to be bigger. Let's call that air resistance, the parachute. So part A says compare the forces. That's a fancy way of saying do a free body diagram. And I'm comparing them. I'm pretty sure air resistance was bigger than gravity or I'd die. B says write a force equation. Who's winning? Air. Who's losing? What does part C want me to find? How would I get F air by itself? Oh, plus the mg over? So you're saying ma plus mg? Double check. Do I know m? 90. Do I know a? What? Oh, I see a meters per second squared. Yes? Plus, do I know m? 90. Do I know g? Again, don't put a negative in here. We took care of the negative by going winner minus loser. Just 9.8. What's the force of air resistance? Let's go to 3 sig figs, 1.02 times 10 to the third newtons. Okay. Now, this was bugging Doug, I could see a little bit, because he was saying, okay, Dueck, I get that you're accelerating up and air resistance is winning, but you still came down. This is why I said air resistance is so tough. The split second this moment occurred, because I'm accelerating up, I'm really slowing down. Which means as soon as I slow down the slightest bit, air resistance just got smaller. Which means now my upwards acceleration got a little smaller. So now I'm not slowing down quite as much, but I'm still slowing down. So air resistance just got a little bit smaller, which means, in fact, eventually you're going to find you reach a point where the acceleration is 0, where air resistance and gravity are exactly the same. And with a parachute, ideally, that occurs when you're accelerating, you are changing your velocity. With a parachute, ideally, that occurs when the velocity is survivable, not terminal. Not going to kill you. That's how a parachute works. But that's why we really, Cole, aren't going to do a lot on air resistance because, again, as soon as you've calculated it, you're wrong. Because a split second later, it would have changed the situation because it would have changed the speed of the system, and now air resistance is different. So we'll treat it situationally, Amanda, sort of like we treated friction last year. We pointed it in the opposite direction and said, solve for it indirectly. Oh, good. I figured I would have done a rant. I wrote here, the force of air resistance actually not a constant value. The force gets larger as speed increases. And eventually, a falling object will reach the point where the force, I need to fix that, the force of air resistance equals the weight, equals mg. You reach the point where F air equals mg, and we call that terminal velocity. Now, I can control F air by another means. I said F air depends on two main things. How fast you're falling, but also your area. All a parachute does, Logan, is it really increases my area, and therefore it makes F air much bigger, so that my terminal velocity is survivable. Survivable. Example 8. A parachutist jumps out of an airplane and free falls. They reach terminal speed, and then they maintain that speed for a while. They then open their parachute. They quickly reach a different terminal speed and descend to the ground. Sketch a velocity. You know what? I want you to cross out the word velocity. and replace it with the word speed. The reason is, Tanisha, what direction is the velocity when you jump out of an airplane, up or down? And if I say velocity, should I call that positive or negative if it's down? Negative. I don't want to do a graph below the x-axis. I'm just going to call it speed, and we'll do our graph above the x-axis. We're going to graph a speed. I drew v with no vector in meters per second versus time in seconds graph. Specifically, Kayvon, we're talking about vertical speed. I know horizontally in the airplane I'm traveling. I don't care about that. So when I jumped out of an airplane, have I mentioned that I jumped out of an airplane? When I jumped out of an airplane, what was my vertical speed looking like? First of all, I'm in the plane. Am I falling while I'm in the plane? So there's going to be a small section where my speed is 0, about that long. I'm not going to worry, Duncan, about the time scale. The time scale is going to be all garbage. I just want to get the shape right. I jump. Woohoo! What happens to my speed now?
Starts to decrease.
Okay, is it going to start to increase linearly in a nice straight line? Well, if we ignored air resistance, we would have said acceleration was 9.8 and the slope of a velocity time graph is the acceleration. It should be a nice straight line. But with air resistance, when is air resistance at its maximum? When I'm falling the fastest. When is it at its minimum? The split second I jump. So actually, it's going to be a steeper slope when I jump, and there's where I'm in free fall at terminal velocity, that horizontal section. Kind of half a parabola with an extended straight line, sort of. Okay? I pull my parachute. What happens?
Increase air resistance.
What happens to my speed then?
Decrease.
It decreases. But you know what? I think, again, air resistance will be at its maximum right when I pull the parachute. I think it's going to look kind of... There's my terminal velocity. And the reason I said this scale is all garbage is, Stephanie, I was actually falling on the parachute for a couple of minutes. I really should keep going off the page because that speed stayed for quite a while. I'm not interested in getting the scale right, Cole. I just want the shape right. And then eventually I hit the ground. Ideally, something like that. Sort of like the side view of an igloo, kind of. Sort of like the side view of half of a ping pong paddle on its side, kind of. Whatever. More of a thought exercise to help us wrap our brain around stuff. Okay?
You said air resistance would be at its max the moment you pull your chute, correct?
So you're arguing with me correctly, I think, that I should do this. At its maximum would be steepest, and then like, is that what you're saying?
Yeah.
I agree with you now that I think about it. Good call. I'm not going to give you one like this on your test. Again, air resistance, Chelsea, is complicated enough. I talk about it because it's kind of cool, and I think kids are kind of interested in free fall, and you've been on rides that do the elevator effect. Okay, cool. You've thrown things, you've seen things drop, you've thrown paper airplanes, you've seen air resistance in action. It's really a complicated force that you really need calculus to deal with. You need fluid dynamics, which I know nothing about except for what I've read a little bit of. What's your homework? And then I got a couple of videos. Oh, it says, speaking of free fall, Mr. Dueck has a video. I showed it to you last class. Have I mentioned I jumped out of an airplane? Homework. Totally number 1 is fair game. Totally number 2 is fair game. 3 is fair game. 4 is good. 5 is good. 6 is good. You've assigned everything so far. Yes, I know. You guys can choose between number 7 and number 8. We can either do the spaceship or we can do catching the ball because they're really the same question. In both of them, I see a mass, I see a velocity, and I see a stopping time.
Spaceship.
Spaceship? Okay. You see what I mean by they technically look like the same question to me? I think. 9 is good? Did I assign 10 last time to my block Cs? I can't remember. I know I flip-flop on it every single year, so give me 1 second and let me check. Block C, I didn't assign number 10, so I guess I'm not going to assign number 10.